Hello everyone. Today I'm going to talk about the aspects of microservice interactions. And you might wonder what does Death Star is doing on the screen. Um, I put this image here because microservice architectures are also often referred to as Death Star architectures. This is coming from these very complex interaction diagrams that were generated in well-known microservice infrastructures, like you can see on the screen. The left one is from Netflix, the middle one you can see from Twitter, and the right one is from Amazon. So having this huge amount of network communications has its own implications. And that's why I think it's very important to understand the the upcoming challenges of a network communication at such a large scale. So that drove me into this topic, into this area, and encouraged me to look behind the scenes and understand the details. And that's how this presentation was born. So the first section, let's talk about the reasons, the driving forces that are affecting these communications channels. But first, I would like to just have a little recap on what are the main characteristics of the microservice architecture style and why are we doing this overall? What's the benefit if we are doing it well? So one of the most important aspects of these things is that microservices are independently deployable. So I should be able to deploy a single service without others really noticing that. On top of that comes another important functionality, autonomy. So this means that a single feature often is mapped to a single microservice. So I'm able to deliver a single feature, a single functional change by just modifying one microservice and ending up in one deployment. What's also important is that microservices are polyglot. Um, they're also polyglot in terms of database usage or database technology choices, also in language choices, but also in other technological aspects. So let's say if I want to come up with a JVM upgrade, I don't have to upgrade all the services all at once and then deploy them in a single coordinated huge deployment. I'm free to go with a single service only, and then other teams owning other services are also free to deploy when they think that's suitable. And that goes on with other technologies. So, for instance, if I want to change from traditional REST-based communication to gRPC, same thing applies. Okay, so for this to work perfectly, we need one single ingredient, namely network calls. So you can introduce dependencies between services in many ways, but a network call is one of the most efficient way of doing that. So if you have dependencies by using libraries, shared data, or anything else, it won't work as well as network communication, a single network communication. So that's why we need to deep dive into these network calls and understand how we can optimize them. These network calls have driving forces. Now think about driving forces. I think we have around 5 of the most important ones. These are namely latency, availability, reliability, queuing theory, and Conway's law. So let's go through each by each, and let's understand how do they affect microservice communications. First one is latency. Latency has a hard limit. That's the speed of light. So if you take the two coasts of the US, the round trip time for the light to travel through the left side to the right side is 27 milliseconds. Okay, but in practice, we cannot reach this number because the speed of light is also affected by the density of the material it's passing through. So, for instance, in fiber optics, if this would be just a single cable, it's more like 41 milliseconds. I got this from this website I have on the references section, which simulates the expected round trip time in two parts of the globe. Um, so that's where these numbers are coming from, but there are many other pages where they are explaining you the expected round trip time in different data centers for a cloud provider. So in case of AWS, this is realistically more like 50 to 60 milliseconds. But it depends on which region are you connecting to another region. But why is this important for us? So this gives you the minimum latency if you connect from one region to another. So if you want to come up with a multi-region deployment because of various reasons, you always have to think about the data synchronization between the regions. And this will be the minimum latency until data arrives to the other edge. And I say this is the minimum latency because in reality, when you have more pressure on your data layer, work will stockpile up, and this will go up to 500 and 600 milliseconds. So 60 milliseconds is the optimistic duration. So if you want to have a synchronous write, let's say, each synchronous write will have at least 40 to 600 milliseconds of latency. This has to be considered if you are planning to do something which has its own low latency requirements. Also, it's important to understand the correlation between latency and throughput. This comes from another research. So they try to simulate uh, um, two things by creating a fictional website. Um, they measured the page load time and measured the bandwidth, and they were interested in how the page load time varies based on the bandwidth and based on the round trip time. So if you increase the bandwidth, if you increase the throughput, then you will see that the benefits are diminishing very early. Page load time actually maps to around hundreds of requests of latency because roughly that's the amount of independent requests required to load whole page. Okay, but if you try to change the round trip time, the page load time is really linearly decreasing. So what does this tell us? First of all, there is no a direct correlation or direct effect between page load time and bandwidth or latency and throughput. So this means also that if you rely on barely just on the scalability or auto-scaling capacities on your system, that's not going to have positive effect on the latency. So if you want to be efficient in terms of latency, you have to think about other solutions, not just scaling out or giving more juice for your instances. Another thing is availability. I think about the availability, I always think in dependency graphs because that's what determines the availability as a whole. So let's see here a simplified machine architecture. For a single transaction, I need all the components to behave as expected. So I need both the CPU, the memory, the network, and the disk component. So what if we give it each an availability number? So let's say each component has now 99% of availability. This will form a dependency graph and gives us the overall availability of 96%. Just because the combination of the components has its own probability of failure if the individual elements have their own probability of failure. That's how maths work, actually. But if I scale this out to a client-server model, you can see that now I have more dependencies between components. Again, let's say that each component has a 99% chance of being successful. Now the availability will drop to 88.5%. So with each single dependency, your availability will decrease. But it also depends on how the dependency is introduced and in which part of your architecture is introduced. Okay, it depends on your dependency graph as well. You can do the maths by hand if you're interested in the availability numbers. I use my own availability simulator, which is just running a couple of cycles and testing each connection and failing them randomly based on these numbers given. I also have this in the references section. Okay. Now, for reliability, I think the most important use case is a single client-server communication. So let's say that we have a transaction that's changing the state of the whole system. So let's say this is a write operation, for instance. How things can fail. Let's go through them sequentially. First of all, the write operation can fail when client sends the request to the server. Then it can also fail by being processed on the server itself. But it can also fail when server successfully process the write operation and it responds back to the client. Here comes the problem. Client can just simply retry the write operation on the first two cases. But after server successfully processes the write operation, client does not know what to do. You may come over this problem by using idempotent operations or something similar. But in other cases, the resolution is not so obvious. And also, of course, I can fail on client side while the request is being processed. But why it's so important for us? So first of all, that's why, for instance, two-phase commit was not really working on a larger scale. Because if you arrive on a commit phase, if one of the requests is failing on a commit phase, the client or the coordinator does not really know how to proceed because other previous operations are already committed and I just got one single failure. Should I just re-request the failed node to commit its changes again, risking duplicated write or something similar? Or should I just abort the whole operation? Another example is, let's say, exactly once message semantics. So the server always have to acknowledge if one message is processed. If I fail after the message is processed, the client cannot do anything else, just resend the message. And that's why we often have at least once message semantics instead of exactly once message semantics. Mapping, again, so mapping reliability to statistically to more requests. We were talking about round trip time and talking about that, or sorry, not page load time. Yeah, page load time and talking about that. Page load time usually involves hundreds of requests and it needs hundreds of requests to succeed. So let's say we have theoretically a single request that has 99% of the probability of being successful. If we have hundreds of requests with the same characteristics, we cannot just say that less than 40% of the chance will be that the hundreds of requests will succeed, all hundreds of requests. Because we have so many permutations of these hundreds of requests being failed, this drops our probability with around 60%, just for the statistical reasons. We can't really fight maths here. These are the hard facts. So this actually resulted as a couple of artifacts that are, I think, are very popular in the engineering world. One of them is this latency numbers every programmer should know, that's presented in many forms. I like this one. This is coming again from a web page where you have a slider and can change the year and see how these latency numbers have changed. These are the recent numbers. So for instance, if we investigate the main memory reference and the latency for a typical main memory reference, that's around 100 nanoseconds. And the round trip time in the same data center as in a cloud infrastructure is around 500 milliseconds. Why should we care, you might ask? Because these numbers are fast enough. So they're very fast and they improved a lot in the recent years. 500 nanoseconds is something I should not care about, right? So if you, let's say, want to introduce a caching strategy and you need to choose between an in-memory solution or maybe a distributed caching solution because you want to share it with multiple services and you want to offer it as a separate service, think about the round trip time. So difference between the in-memory and the distributed solution, caching solution, is in terms of latency is around 5,000 more if you choose distributed cache than if you choose an in-memory cache solution. Another paper is this fallacies of distributed computing. You can find it in Wikipedia. If you look at the top 3 of these fallacies, then I think it's clear that we covered plenty of aspects of those. But the others are also important. But now I want to talk about something else, talk about queuing theory, and spend a little bit more time because in my experience, how I saw people in the engineering area are not really familiar with queuing theory and not really thinking in queues. But in practice, I think queues are everywhere in a modern architecture. At large scale, also in small scale. So it's very good to understand the basics. So here comes the basics of queuing theory. When talking about queues, I think you can think about the simplified model that you can see on the screen. So you have a queues of these orange marbles, a single queue of these orange marbles that needs to be processed. Then you have something on the right side that is processing the marbles and producing these green marbles on the right side of the screen. And then you have these metrics around the queue that determines the queue performance. We are interested in these 4 mainly. So there is execution time needed for a single node to process an orange marble and create a green marble. Then there is the departure rate, meaning the rate of green marbles being processed. Then we have the latency that requires duration of either a single marble traversing through the queue up to the right side when it becomes to green marble, or the overall duration required for all the marbles being processed. And we have then the arrival rate on the very left side, which is the rate of the orange marbles arriving in the queue. So the most basic question is, what happens when the arrival rate is much larger than the departure rate? So this happens with us all the time, actually. So if you have something that's publicly available on the web, you don't have control over the user base and their usage statistics, and often have to operate in this area. So in this case, if you just accept all the requests and try to process them, you are guaranteed to fail after a certain period. And you have to introduce something, right? This something is called back pressure or rate limiting. Okay, so often in the edge, you have a rate limiter service that determines which endpoint is limited to what sort of throughput and tries to keep the right side or protect it from a higher rate than usual, and tries to introduce some sort of a logic on limiting those clients who maybe misbehave or limiting requests to a specific service overall. So this is an important topic, and we will talk about it a bit more in the second half. So coming back to queuing theory, let's have a couple of practical examples. So in this simplified scenario, the execution time is 100 milliseconds. So what is the throughput in this case? We produce 10 marbles per second because we produce a single marble each 100 milliseconds. The overall latency for processing all these 8 marbles is 800 milliseconds. It's 8 times 100 milliseconds, right? It's very simple. Now, what if I try to parallelize now and have a single queue but have doubled the workers? Now I produce 2 marbles in each 100 milliseconds. So I have 20 marbles per second as my throughput or as my departure rate. The latency is also halved because now I can produce 4 times 2 marbles in overall in 4 times 100 milliseconds, and that comes up to 400 milliseconds. Okay, but what if I divide the work like that? So instead of having a single parallelized operation, I try to split the work uh, in 2 halves, which can be finished in 2 times 50 milliseconds. Let's see the numbers. Now I can produce a single marble within 50 milliseconds. That comes up with this throughput as before, as in the previous example, as 20 marbles per second. So I still improved, doubled my throughput. But how is my latency changed? My latency will be still 800 milliseconds because I need a single marble 100 milliseconds to travel through from the left side to the right side, right? I need 2 times 50 milliseconds for a single marble to become orange marble to become green marble. So interestingly, latency did not change, but throughput increased. And that's the magic, I think, of these reactive libraries that are becoming very popular these days. So by simply declaring my work in a different way, it allows me to have higher level of parallelization by splitting my workload into smaller chunks and introducing more queues and processing them in smaller units overall. It increases my parallelization even though I'm not aware of that, because in the code everything seems sequential. All right, so if I have a bottleneck, let's say, then the numbers are changed as following. So I still have 10 marbles per second because the bottleneck keeps me from processing a single marble within 50 milliseconds, and it just allows me to have a green marble in every 100 milliseconds because that's where the bottleneck is. And in total, I need 100 plus 50 milliseconds for a single marble to go through. So my latency again is increased to 1,200 milliseconds. There are many other scenarios, but I think you can do the maths easily in your head. I have a few formulas that maybe not really precise, but it's enough to me to understand what's going on. What's really important, as you can see, that the throughput is not really depending on the queue length. It's not. It's behaving a little bit differently than the latency. So as you seen before in the example, in the where I was talking about this research with page load time and bandwidth, throughput and latency does not really depend on each other. What other things can you do with queues? What's very important is that for each queue you can provide its own quality of service. So these numbers can be independently provided for each queue. So let's say if you have a producer, a single producer like the one who is producing the orange marbles, which needs higher demand, you can separate it to its own dedicated channel, and it won't affect those which are producing want to process blue marbles and yellow marbles and won't choke the system so easily with its own requests. So by separating them to different channels, you can offer a separate quality of service to each channel. And this can be done in a couple of ways in microservices. So first of all, a single service concentrates on one um, specific workload, and that forms its own queue and its own special way of optimizing for that kind of workload. It's independent from other services, but can be introduced also in a single service if you have messaging and use multiple channels for multiple clients. I will have again a detailed practical example of how we use this feature. So about Conway's law, just very quickly. Thinking about Conway's law, I always just consider how many scenarios we have with communication, with single communication considering teams. Okay, so in this scenario, in the two parties, in the two sides of the communication, a single team is controlling the change for each side. This is the easiest scenario because you can do whatever you want. You can proceed as fast as you would like to. Now we have these scenarios when a shared responsibility is on one of the other side. This is some sort of an anti-pattern. This is not frequently used. Only companies use on those occasions when they don't really need to change so many things in a legacy service or they don't really know how to separate the ownership of maybe a bigger chunk of code. This slows things down radically. This is when you have to be very careful. This is when you need to introduce non-breaking changes or have the legacy endpoint live for a very long time. Now, there is this more healthier scenario when you have multiple consumers and you are the producer side or you are the consumer and there are multiple producers. This can happen in many situations. What's important to understand, I think, that the service ownership does not necessarily come with the schema ownership. You are free to move the schema ownership to the other side and to the and back and forth, however you feel it's more suitable. This comes handy in a couple of situations. So let's say that this is an event-based system, and who should control in this case the schema? The message producers who are producing the events themselves. Should they tell for the other teams that, yeah, there's going to be a schema change and be aware of that and then just contact all the other teams, see if they are ready for accepting the new events? Or should we do it in a different way? Should the consumers be controlling the schema ownership and tell the producer that, okay, we are expecting these kind of messages from now on. We are accepting this kind of change, but not ready for another change, and so on. There are tools and techniques on how to do this, and it helps the visibility, it helps testability, helps with many things. There are also schema registries that you can introduce. You can switch from something that's schema-less, like a traditional REST-based um, API, which is offering just simple JSON-based communication, to a more conservative way of communicating, like using strongly typed APIs like GraphQL, gRPC, or maybe introducing schemas into events and messages as well. And there is this most complicated scenario when there are multiple teams in each side, the producer and consumer side. That's when you need something more advanced, or the most advanced things for controlling schemas, something like schema federation. That's storing different versions and kinds of schemas and schema changes in a controlled way, most preferably in a measure controlled way. Okay, so This is where the first part ends. Now I would like to just quickly introduce you the toolbox or the things that I consider and jump right to the next section when we will talk about practical examples and situations that I faced, and I would like to guide you how we improve the situations each by each. So the tools that I use usually. You can do something like cqrs, um, meaning that you can separate the write and read path if you need something special on the read side or maybe something special on the write side. Then we talked a lot about schemas. You can introduce contract-based testing. It helps to move the schema ownership to the other side. Then you can introduce caching. We saw in the latency part how caching can improve the latency. With caching, you have to think about data freshness, and multi-write helps here. Um, I call multi-write something that keeps the cached values fresh in a proactive way. So if you grab a fresh value from one side of your system because one of the clients needs that, you need to proactively write it to other cache instances to keep the data fresh and reduce the number of cache misses. Then you can switch from synchronous to asynchronous communication by keeping the original API, by introducing polling, by introducing maybe a synchronous API that sends forward the request to a message queue and then just sends a simple response back to the client. There are also design practices or design principles that you can rely on, like cloud native and 12 factor. I won't cover these, just thought it's good to mention them. Auto scaling can be effective in many ways. Um, and auto scaling has a positive effect on throughput, but not on latency, as we discussed. I talked about back pressure back in this section when talking about queuing theory, when you have higher arrival rate than departure rate. If you need large-scale transactions, then you can introduce sagas in a microservice architecture. You can do it in a couple of ways. You can control the transaction either by using orchestration or choreography. You can introduce a service mesh. I think service meshes are important because there are many ways to fine-tune the communication channels inside service mesh. It improves your observability. Um, it helps you with certain kind of security aspects, and you can introduce many resiliency patterns, resiliency configurations inside service meshes, like circuit breakers, timeouts, retries, and so on and so forth. You can be conscious about your technology choices. So, for instance, if you choose gRPC over REST-based, traditional REST-based communication, you can expect lower latency because usually gRPC has less round trips during a communication, during a request response. And payload is smaller because it's binary based, so probably you have more throughput. Messaging has many patterns, so if a synchronous communication is not enough for you, then you can introduce messaging in one of the sides, switch from synchronous to asynchronous communication, and then you are free to use all those messaging patterns, which will increase the robustness of the communication itself and maybe help in a specific situation. If you choose your concurrency model well, it will have higher throughput, probably won't have a positive effect on the latency, but have higher throughput with less resource. So it will introduce more channels, more queues, but not necessarily more threads. This is very well used and I think a well settled technology coming in with reactive programming or coroutines. So they are good choices if you want to save resources with your communication. Then there are these resiliency patterns. I think many people know because they are widely used in the microservice world. Also, service meshes offer them by default. There are also libraries that are providing uh, most of these. So there are circuit breakers, bulkheads, retries, timeouts, just to name the most important parts. Timeout comes with all the libraries which are communicating with the network. Then you have observability to just review the whole and understand if you are improved or not. Now let's jump to the example part. So I will pick a couple of practical examples that I've met, and I will go through how, in a specific situation, things are improved with what kind of practices. Okay, so one of the examples I like is coming from the distributed database called Cassandra, and this technique called rapid read protection. This is how it works. So let's say a client needs to read the data from the database, and it needs the data to be up to date. So then the client goes to this so-called coordinator node that you can see on the top left, and the coordinator node then they gets the data from each replicas, then aggregates the data based on its freshness, and then sends back the up-to-date data to the client. Now, what happens if one of the requests is being slow? Instead of waiting for the request, the coordinator node is going to fire a so-called backup request, hoping that this backup request will finish faster, and hoping that the coordinator node will send back the data to the client also faster. Why is this happening? Isn't this just a waste of effort and just a lot of complication? Shouldn't we more efficient if we just wait for that request to finish and just fail if there is no answer? So if you think about availability again, let's say we have 99% of availability for each node to be successfully responding the payload to the coordinator node. In this case of 1% of the chance when we have failure, we will still have 1% of chance or 99% of the chance to be successful if we use a backup request. So the overall availability for this simplified scenario, for this simplified query is increased. It's now around 99.99%. Okay, and if you would also investigate the P99 latency numbers, you will also see a decrease if you compare to the scenario if you would turn this off, because we won't see timeouts that often. It's true that overall we have some situations when it would have been better to wait for the answer to arrive instead of just going on with another backup request, because that can also fail. But overall, at large scale, statistically, we are still better, still performing better. Okay, now the other use case is coming from a scenario where I had to design a system with a read-heavy workload, a very read-heavy workload. And the writes were theoretically like almost immutable. They were not changing at all. So we just created objects in this part of the architecture. We were hardly changing or updating them. I needed to reach a very low latency requirement. So this, as the result, meant that I had to prevent scenarios when I had to deal with cold cache, with something that comes and reads up all the data from the database. And I couldn't use any distributed cache solution for this situation because it would have hurt latency so much that it would have been impossible to meet this low latency requirement. Here comes cqrs in the play. So instead of just trying to put everything in a single service and try to fine tune and optimize that and try to benchmark things and try to find the bottleneck, and improve, you should think in a larger picture, and you should use the techniques that I talked about. So we separated the write path that you can see on the left because we are not really interested in the latency of the write operations. It was not critical for these writes to happen immediately. So we went on to the AWS queue and then continued the write to the database side. And it was true that we were having large write workloads, but because we were writing to a queue, it helps us to keep the write operations on the DynamoDB lower, and iron out these bursty operations and help to keep the write capacity unit lower than usual. Now for the reads, we introduced a distributed in-memory cache solution with Hazelcast that was also replicating between each read node. So this resulted as a couple of things, like if I scale out and have a fresh read node, it should not come up with an empty in-memory database. So immediately when a new read node comes in, it starts synchronizing with the other read nodes, which helps the data being fresh. Also, when we have a cache miss in one of the read nodes, when it finds new data by going to DynamoDB, it immediately proactively starts replicating this data and writing it to other read nodes. So that's how we solved keeping the cache warm with multi-writes, with using replication as well. And the write instance or the write service responsible for the writes had nothing to do with Hazelcast, was not aware of this complicated configuration of the in-memory cache solution. Also, the read instances did not have to have the SQS-based libraries and did not have to do anything with SQS at all, with that communication, with the access, and so on and so forth. So this simplifies your architecture overall even further. Okay, now with client libraries, I have a couple of stories. I treat client libraries as a double-edged sword because I think it's very hard to design them in an effective way. They are not considering all these extensibility options, and not all the features can be turned off. In this specific client library, this library was included in many services as dependencies, as default dependencies, and this was the only way of use a specific shared feature of the whole architecture. This specific client library downloaded a zipped archive at startup from Amazon S3 and started decompressing it during startup just to get the configuration data required for this library to work effectively. This was the single bottleneck for the startup of the whole service. And unfortunately, hidden behind the scenes, it messed up the startup for all the development environments. So all the developers suffered from the startup penalty introduced by this client library. Unfortunately, there was no way to turn off the library itself because the maintaining team wanted to keep it as simple as possible. They did not want anyone to change certain functionalities of the library, and they thought that if they introduce too many features for the library for customization, then they will have hard times with the maintenance of the library because there could be plenty of ways teams are using that. So how we solve this problem? We just, yeah, okay, sorry. So another issue with client libraries was that it often messed up the deployments. So because health check was depending on the functionality of the library itself, if there was failure during downloading the data, the service often just timed out and failed to meet the health check requirements that messed up the deployment. Okay, so even deployments were negatively affected by the usage of this library. So how do we solve this issue? We just simply shift things on the left side during delivery, during deployment, what this meant for us, we just picked a mock S3 solution, containerized that using Docker, and used it as a sidecar container. We prepared two mock libraries um, in the mock storage. One of them was empty, meaning that it was very fast to download and extract that, and the other one downloaded the same way downloaded the data from the S3 bucket, then extracted that, and just had the certain configuration which was meaningful for us, and we put that into this mock container. The thing why this worked was very simple. It was because they did not have a feature switch or a kill switch for the library itself, but the URL was configurable because each specific environment had its own bucket configuration. Another way other teams solved this problem was introducing some kind of programmatic proxy, which was still trying to keep things on when this connection was not available, and behind the scenes try to kick in this client library to retry loading up the data and delaying the downloading of this data that was important for them. Okay, another technique that I want to talk about is what I call region pinning. This might be not necessarily the appropriate name for this technique, but this is how everybody was using that, so this is how I refer to that as well. Imagine the following scenario. We had to migrate to the cloud with our own whole architecture, the whole system, and then had to make it multi-region. And one of the problem was what we found was with shopping carts. So each service was there was not a dedicated shopping cart service. Each service was managing the shopping cart through a shared database, namely a shared Cassandra cluster. So each service was reading the shopping cart from the shared Cassandra cluster through a library and was updating the shopping cart when was necessary through a shared library, and then putting to this the data to this shared database. Okay, and we could not really rely on the replication lag because it was uncontrollable. So the minimum replication lag was around 60 milliseconds, but in practice, if you have more pressure on the database, this could have been easily increased to 500, 600 milliseconds based on the load itself. Okay, um, and we were afraid that these shopping carts will disappear. So if one of the service or the traffic for one of the service is put to the right side during the user journey, we were afraid that when the shopping cart was being loaded because of the replication lag, it was not available, it was empty, or maybe it's not containing the up-to-date changes. So how do we distinguish between users that have up-to-date shopping cart in the left region from those that, let's say, don't have yet shopping cart or started their journey on the right region? That's where region pinning is coming into play. We flag the originating region for each user by using a cookie. And when moving those certain users who need their shopping cart but started their user journey in the left region to the right side, based on this cookie, we reach out through this white line, paying that 60 millisecond latency penalty, but loading the data consistently and having the shopping cart. So with this way, we won't penalize all the users because we are not going through this white line for all the users all the time. We just proactively select those users which needs more consistency, but should be okay with this latency increase. In another example, I was using the same approach when I was designing an auction solution. So here we had to keep a strict ordering of the biddings. And no matter which message provider I looked at, I figured out that there is no way to keep the messages in order when I rely on synchronization between regions. Okay, so if the auction started on the left side, in the Kafka cluster on the left side, and somebody wanted to participate in that auction on the other region, they had to pay for this latency penalty proactively, but write on the for to the Kafka cluster still on the left side. And then for others, for other services or participants which were not latency sensitive, the data was still available maybe later in a synchronous way through the mirror maker on the right side, so they could have continued um, processing this data or maybe showing this data a bit later. But those who wanted to participate in bidding had to write consistently on the same region as the auction is originated. This is similar to the things we used to in the gaming world. So if there's a game started in one certain region, then when other players are participating, they have to consider the latency penalty and maybe not perform that well. But this keeps the game consistent. Okay, the last example is coming from the journey of optimizing a single service in a couple of iterations. So I would explain the behavior and the functionality of the service a bit more at first. Okay, so this service had two endpoints. First of all, it was a very simple key value store. Um, you can see the value endpoint on the right side of the service, which reads the values for a certain key given. Okay, and that's coming to specific DynamoDB table, which has its own read capacity unit defined. But we have also another endpoint. This is how things were when we got the service, when we started maintaining that. So this is how what we kept. This was the endpoint of the recent keys. What this endpoint did was that it gave back to the client the keys that were being accessed by that specific client in the last 7 days. That went off to another table, which was statistical table that you can see on the left, which had their own read and write capacity unit defined. Now, both tables had auto-scaling configured, but there was a problem, as you can see on the right side diagram. There were one specific client which was firing up 15,000 requests to this values endpoint because it had 15,000 keys in this usually being used, and it went with one single request to this recent keys endpoint, found that in the last 7 days it was using these 15,000 keys, and iteratively it went through all the keys, bashing sequentially these values endpoint, increasing traffic. And the DynamoDB auto scaling was not catching up. Um, there was a time window defined by this red line that you can see on the screen when DynamoDB was throttling because it failed to meet the capacity needs for the traffic. And unfortunately, when traffic burst was over, auto scaling increased for DynamoDB, but then the increase decreased immediately after that. Okay, now one of the problem was that the statistics table was written sequentially before the read happens when getting the values, just to keep the statistics fresh. So during maintenance, we had to keep the write capacity units the same as the read capacity units for the two tables because auto scaling was hard to fine tune and because the if the write capacity units are lower, we are just failing by writing the statistics table and the reads were also failing. So what we did first was separating this critical path from the rest. So we put the update operation just in a different thread and just deployed the solution. Things worked a bit better than before, but after a short period of time, there were other problems. we've seen that for some reason the memory consumption of the services were increasing, and the container orchestrator started killing these services themselves. And the reason or the reason of that was in the flow of the implementation. This was the way we created the thread that was dealing with this change. This is in Java, but you don't necessarily have to understand Java to understand this use case. We just created a separate thread that has a separate queue that is processing these requests when they are coming in and updating the statistics table. Now, where comes the problem? What do you think? Where is the problem with this implementation that's causing the memory increase and the killing of the instances from time to time and restarting them? Well, it's not obvious because of all the implementation details, but this is the single place when there is a problem. So very often Java threaded or old school threaded implementations are coming with this unbounded queue, meaning you have a limitless queue. And what happens when you have an increased arrival rate and your departure rate is much lower? You will have this unbounded queue filled up, your latency will increase up to infinity, and your memory consumption will also increase up to infinity, up to where you can hold this data, because you have a very huge queue sitting there for no reason. And actually, this is not even true because this is not an unbounded queue. It's not erasing data automatically. It gets full. It's just a very, very huge queue because it's implemented by using the maximum value Java is declaring for integers, right? So we can do better than that. So we reiterated with this implementation, and we just simply changed to a more sophisticated solution. We started using resiliency for J, which is a library for implementing resiliency patterns in Java. And we wrapped the call with a bulkhead, which now had a limited queue capacity up to 25 items. And when that queue was full, bulkhead was throwing an exception. Now, we could have exception because of two cases. First of all, because DynamoDB started throttling, it's just rejecting our requests, or the bulkhead was full. So we wrapped this whole thing, this whole call into a circuit breaker, and the circuit breaker just opened when it saw these two exceptions, give the whole thing a pause, and then started again updating the statistics. And this helped us recover from the situation as from before. We did not have these memory issues. The clients did not really notice anything at all. And we looked actually at the metrics of the circuit breaker, looked at the statistics of when they were opened up, and it was not a big number. So statistics not really suffered because of that. And the normally behaving clients could just keep up with their own normal operation, maybe having a couple of more cache misses than usual. But with metrics and with this solution and investigating metrics, we thought we were fine. So we dropped the write capacity units finally for a statistics table that did not have to match with the read part of the values table. Okay, now, but we really wanted to reduce also the read capacity unit for the reads. So again, let's go back to the baseline and talk about what we have with a bit more detail. So we have 15,000 items coming in, 15,000 requests, like almost instantly. And then we had these services packed in an auto-scaling group that was CPU based. And then DynamoDB was throttling and giving us back HTTP 400 errors on any case when we reached our read capacity unit. So what if we do retry? So what if we have this HTTP 400 errors? We just retry the request and hope now that the read capacity unit was catching up. Unfortunately, this was not introducing any fairness to this whole solution. So when this misbehaving client came with these 15,000 keys, it just choked the whole system with its own requests. Other clients had to wait until DynamoDB was catching up to get their own answers. Okay, so it was not introducing any fairness for this whole scenario. We wanted to do better. We tried also built-in rate limiting, but we did not go into production because for obvious reasons it was not working very well. So you can introduce a quite okay-ish implementation with resilience for J that also has rate limiting. It's quite precise. So you can have 40 operations per second for each instance. Now with 2 instances, you have in total of 80 operations per second. Now when the auto scaling kicks in immediately, you have another instance having 40 operations per second, which now also increasing your rate limit and your capacity, which is not true, of course, because the original capacity is determined by the DynamoDB's current capacity and by its auto-scaling characteristics. Okay. We tried many other things, but one of these was this one. Obviously, did not work well. We could have put rate limiting into something that used centrally, namely into the service mesh. So in this case, Istio was also offering rate limiting. It was using Redis to keep the states of each client to control the rate limits. Problem was that it introduced an API change. So instead of giving these requests a pause or maybe slowing down the clients which are misbehaving, similarly to what Backpressure does, it immediately gave them another kind of HTTP response, and we thought that's something that's going to cause more trouble than solve solutions. So we did not go on with this change. Instead of that, we went back to queuing theory. So if we simplify this into a simple queue, this is what happens. So you have 15,000 items coming in. You have a couple of executors there on the right side, and the throughput. And to determine the throughput, you need the latency. So the overall latency was equal to the timeout configuration of the client, which was not easy to figure out, or not difficult to figure out, sorry, because it was the default being used. I don't know where this number is coming from, but for every library, it looks like timeout is 30 seconds. So we had 30 seconds to consume and process these 15,000 items. This gives us the overall throughput of 500 operations per second, regardless of the number of executors. So with two instances working on that, we need to complete each operation in 4 milliseconds, which seems to be nearly impossible. We do not really want to bother with optimizing the whole thing. But if you scale this out to 5 nodes, to 5 workers, it's a more user-friendly number. It's now 10 milliseconds, which seem to be doable. So we think that if we can slow down these 15,000 requests to not to be processed immediately, but instead of them to be processed within 30 seconds, or close to a number that's 30 seconds, with 5 workers, if we have the execution duration of 10 milliseconds for each worker, we can do it in a sensible way. So we tried to find a technology that allows us to do that. We were looking towards rabbitmq because a couple of very interesting features. RabbitMQ has this queue overflow behavior. So if you set this overflow setting for a queue, then it will immediately reject and not consume those requests that was put into the queue. So it will wait. I think it will wait on the client side until the queue still has capacity and until the consumers are catching up instead of failing them. It's failing after a certain amount of time. It also have another rate limiting or flow rate behavior, but it's bound to the memory and CPU usage to rabbitmq, what you can see on the middle left on the screen. That's very hard to control. This is not what we were looking for, but still was quite promising. Then what's important is that you can define your prefetch settings by queues that you can see on the top right corner. So you can have a single channel of connection that's connecting to different consumers to different queues and have different settings for each queue. So if you have one of the clients coming into one queue, you can have a specific configuration for that single queue. Now for another queue, you can either have the same or different configuration as well. And you have many options to acknowledge the request. So when DynamoDB starts throttling, so you just simply acknowledge or not negatively acknowledge the or reject the message from the worker side, and you can retry with the next iteration or with the next worker. So here was our setup. Basically, we had a service or the array of services. Now, having an auto scaling group. This was using a so-called fake boundary. This is how I call that. Maybe there's a better name. And instead of being synchronous, it was asynchronous, but it used request reply queues. And we separated the request by each API key. So each client fortunately forwarded their own API key in the header. And in each queue, in each channel, we had the same configuration. The same configuration of overflow settings, the same configuration of prefetch rates, and each worker connected to all the queues at the same time and have their own auto-scaling group. Creating a new queue if we saw a fresh API key was not a problem because the configuration was in the service itself. So this had something like global configuration available, and though connecting to a new queue when we see a new queue from the worker side seemed to be a bit more complicated, but doable because RabbitMQ is offering management API as well, which helps you discover if there's a fresh queue, and opening up a new connection seem to be and having a new unit which is consuming that connection seemed to be not a big deal. And then we could connect to DynamoDB and reject the request if there's throttling. But hope that this will have the effect what we desired for. Again, we need to slow down misbehaving clients. So if there's more orange marble coming in, we have to say after a while that orange marbles have to wait while processing the blue and the yellow marbles in their own pace. And this is the metrics that I've got. Unfortunately, this is not from the real scenario. I had to rebuild it in a sandbox for certain reasons, but it's available under my GitHub profile, so you can try it by your own if you want to. So this was the baseline of direct reads. Now directly coming from the service of the database, you can see that we have the throughput of 300 operations per second, and we complete all the reads in 15 seconds. And the response time is around 10 milliseconds. This is quite good because it's quite close to this scenario with 5 workers that you want to reach. And the response time distribution is very tight. So it's everything from going to 0 to 1.8. I don't know what the unit is. Maybe this graph is messed up. Sorry for that. But for the other diagrams, you can see that these numbers change at least. So with single worker, what we can see now is that rate limiting is working as expected, or the back pressure is working as expected. So now instead of doing all these reads within 15 seconds, we just give it a pause and we do it instead of that in, I think, 2 minutes. Yeah, in around 2 minutes. So it's not reaching that 30 seconds goal what we aimed for, but it's giving the request a pause when we have more process than what we want to. The response time average is a bit higher than expected. But at least we have just a single worker, so at least we have this set up as we want to, and you can see this from the response time distribution. So the response time distribution now is going to up to 14 units. So it's better than it was before. And now with 5 workers, we tried it out also with 5 workers. We saw that with 5 workers, we succeeded to reach our goals. So this exactly takes 30 seconds as expected. And interestingly, in one point, we measured even a higher throughput. So the original throughput was very close to the baseline, and in one case, it was a bit even higher, even 500 operations per second. It also shows that throughput has nothing to do really with latency. It has some relations with latency, but we are able to meet even higher throughput even if we have higher latencies, so for some of the clients, for some of the channels. And the worker execution time and response time now, especially if you see the worker execution time, you can see that now it's getting short to getting to 10 milliseconds at the end, where we want it to be. And the response time distribution is again a bit better distributed than before, so this was quite promising for us. So that's all I wanted to say and present to you. Thank you so much for listening. Again, I was Oresztesz Margaritisz, and I work as an Associate Chief Software Engineer at EPAM. If you have questions related to the things I talked about, just feel free to reach out to me by using either Twitter or LinkedIn, or feel free to visit my GitHub profile. But I have an availability simulator that helps you to get these availability numbers that I was talking about, and have this example sandbox of back pressure and rate limiting I was presenting to you. And I get plenty of references. If you're interested in more, just feel free to look at the end of the slides and discover a couple of the things I talked about even in more detail. Thank you very much again for listening. I hope you had a great time and learned something new.